Good morning, good afternoon, everyone. Welcome to our 5.2 update webinar. I'm Annalie, I work for Vast Data, and I have Howard Marks here with me today. I just want to go over if you all have any questions. You can ask your questions using the Q&A tab on the right-hand side of your screen panel. Feel free to throw in as many questions as you all want in there. We will have our team answering them. If we don't get to your questions before the session ends, we will follow up with you all. You can ask your questions anonymously. Just check that hide your name box at the bottom of that panel. Today, I want to introduce to you our speakers. Today, we have Howard Marks, who works for Vast Data. Years of experience. Howard, thank you for being here today. And then we also have Dave Graham. He is a technical marketing manager. Thank you for being here as well, Dave. So we're excited to hear your all's conversation, and I will hand it over to you all.
Thank you, Analia. Keyboard bounce gets me at the beginning. So 5.2 is a relatively major release because we've introduced some new architectural features to the Vast Data platform. So in 5.2, we have support for e-boxes. The E stands for everything. We have improvements in how we handle storage class memory to increase both resilience and performance. We've doubled write performance again through some of those SCM improvements. And so that means that since 5.0, we have about a 4 times performance improvement for large writes. And then we have additional improvements across the platform. S3 event publishing and moving the limitations of per tenant quotas and of quotas and QoS to be able to apply to tenants as well as users and folders. Improvements in the data space, the big one here is synchronous replication, lets us achieve an RPO of 0. We've extended the global namespace with some enhancements, and we're enhancing our cloud story with the first true clusters in a cloud provider at Google. And then for the Vast database, we've made it easy for you to import data from your existing data lake through a GUI import table from Parquet function. But really the big news is the introduction of e-boxes. When we came out with DACE, we based our architecture around a highly available D-box that put SSDs on the cluster's NVMe fabric in a redundant way. That was great while we were dealing with relatively small clusters of 50 petabytes or smaller, because having the SSDs in that highly available enclosure meant we could not worry about enclosure failures, that we could only worry about SSD failures when we were doing things like striping data across the SSDs. As we're moving into larger environments and new environments, we have introduced the e-box. The E in e-box stands for everything, because each e-box performs both the functions of a C-box and the functions of a C node and the functions of a D-box. That is, it runs the C node container that provides all the intelligence for the Vast Data platform. It also runs D-node containers that manage and make the SSDs available to the NVMe fabric. What hasn't changed is that the server in which the SSDs happen to be loaded does not have any ownership of those SSDs. Every C node container communicates using NVMe over fabrics to the SSDs directly in the other e-boxes. So it's still a shared everything environment, even though we've re-aggregated to some degree compute and storage. And the reasons we've done that reaggregation are multifold. First of all, we had server vendors who wanted to work with us and didn't want simply to provide C nodes, but wanted to provide more of the system. Second of all, we had cloud providers and other large customers who have standardized on particular platforms and don't want to add unique hardware like C boxes to their environments. At relatively large scale, where we're talking about 20 or 30 E boxes, we achieve similar efficiencies to D boxes. And so for those customers, E boxes are a great solution. The big thing to remember about E boxes is that E boxes use the DBox HA data layout. So E-boxes are a solution for hyperscalers and large-scale environments. They're not a mechanism to bring VAST down to a small scale. The minimum cluster size with E-boxes, as with DBox HA, is 11 D-boxes. That's about 2 petabytes of usable capacity. The first E-box to come to market comes from Supermicro. We'll be seeing E-boxes from other server vendors over the next few months. These E-boxes are a 1U box with 12 SSDs. They hold both SCM and QLC just like D-boxes. And of course, the E-box technology is what lies behind the ability to do VAST on cloud and VAST on cloud clusters, because cloud instances are just virtual x86 servers, and vendors like Google and AWS don't have the equivalent of a D-box for us to use. Moving on from E-boxes, let's talk for a minute about how VAST uses SCM. Traditionally, SCM is used for two purposes. About 80% of the SCM capacity in a cluster is used to hold system metadata. Because the system metadata is in SCM, we can make small writes to the SCM, update metadata in place with high performance and low concern about endurance. The other 20% of the SCM is used as the write buffer. Data comes into the system, gets put in the write buffer, later gets migrated to QLC. We have traditionally protected data while it's in SCM the way people have protected caches and write buffers traditionally, and that's by mirroring. Mirroring gives you low I/O amplification, allows you to make small writes effectively. And when we mirror, we have both dbox and dnode anti-affinity, which means that we spread the two copies of any page of data in the SCM as far as possible across the cluster. Data is mirrored in 128 meg pages, not mirroring SCM SSDs to each other. And the write buffer is basically a first in, first out list. So when new data comes into the write buffer, it goes at the tail of the list. As data is migrated, it comes up to the front. Data in the write buffer is basically written in the size of the I/O. If an application does a 4K I/O, we write a 4K block to the write buffer. If the application does a 1 meg I/O, we write a 1 meg block to the write buffer. Mirroring works fine, but it left us with two challenges. The first is that in the VAST data platform, most clusters are bottlenecked by the bandwidth to the SCM SSDs. When you mirror data and you're writing to SCM SSDs, half the bandwidth is being used to write the mirrored pair. And so that means that half of our bandwidth is being used for overhead. The other problem with mirroring is that it only protects against a single SCM loss. In bigger clusters with more SCM SSDs, the odds of more than one SCM SSD failing before before the rebuild completes goes up. In addition, we have traditionally stored SCM SSDs in highly available D boxes. So only failures of the SSDs themselves were a concern. As we move SCM SSDs and other SSDs into E-boxes, E-boxes are not highly available. An x86 server has multiple single points of failure. And so that's going to increase the probability of simultaneous or contemporaneous SSD failures. The fix is to simply increase the protection level. And so we're moving all of the SCM data from being protected by mirroring to being protected by N+2 protection. For the write buffer, where we're primarily doing large sequential writes, we erasure code the write buffer and we triple mirror the metadata so that we can still do small, low latency updates. Write buffer erasure coding, which sometimes is called write buffer RAID, although remember we're doing distributed erasure coding, so RAID isn't quite the right word, appeared in VAST 5.1. We write data to the write buffer using Reed-Solomon erasure codes with double parity. This reduces the overhead from 50% for mirroring to 2/12 for the 10+2 erasure coding we do on almost all systems. 5.1 also has improvements to write buffer locking, all of which combines to boost the write bandwidth by about 100%. A single series D box could do about 5.5 gigabytes per second of write bandwidth in 5.0, and a cluster of series D boxes can do 12 gigabytes per second per D box in 5.1. This is currently only available in clusters for 5.1. We anticipate that 5.3 will make this available as a retrofit. As you can imagine, reformatting data that's already in the write buffer is more complicated than simply creating a write buffer with a new format. And so we generally release things as updates, a release or two after they appear for new clusters, so that we have time to work the bugs out of the basic feature before adding that additional complexity. Note that even with write buffer erasure coding enabled, if you're doing small writes, those are simply mirrored, and the C nodes will pad the erasure code stripes when in periods of low writes so that they don't add excessive latency. In 5.2, we extend that ability to survive 2 device failures instead of 1 to the data metadata. And we simply do 3-way mirroring and write to 3 SSDs, again with dbox and dnode anti-affinity. Initially, metadata triplication is going to be available for eBox clusters. In 5.3, it will appear for CBox dbox clusters. 5.4, 5.5 before it's available as a retrofit for an existing system. But triplication is kind of the classic example that there's no such thing for a free lunch as a free lunch. By writing 3 copies, we suffer some performance penalty as opposed to writing 2 copies simply because it's more work. The worst case, performing IOs on 0-byte files so that you're doing pure metadata operations, results in about a 20% performance loss. In clusters doing real work, it's unlikely we're going to see a performance loss that's noticeable by users. It'll be on the order of 5%. It also means that we have a 33% loss in metadata space because we're now writing that 3rd copy. That could limit the maximum amount of similarity in the cluster. It could minimize the number of files or elements in the cluster. And so work with your sales team to determine exactly how you want to configure a new cluster. Note that 5.1 added metadata compression, which boosted the maximum data reduction and boosted the maximum number of elements per box. So the combination of metadata compression and triplication effectively leave those limits where they were in 5.1. As you may have noticed, some of our big customers and some of the most exciting work going on in computing today is around building AI models. The hardware on which you build AI models is bleeding edge. It's the very latest GPUs running the very latest networking. And the problem with GPU technology is the problem with leading edge technology is it tends not to be that terribly reliable. And so if you're doing a job that's doing important training on your AI model, and that job is running across 100 GPU servers for a week, the odds that one of those 100 GPU servers will crash during that week while your project is running are relatively high. And so the code for generating models does checkpointing, where periodically all of the GPU servers dump their memory to storage so that if something goes wrong, they can recall that memory image, that checkpoint, and pick up from where they left off. NVIDIA generally recommends checkpointing occur no more frequently than once an hour, and that checkpoint take no longer than 5% of the time between checkpoints. So if you're building a system, periodically there's going to be a large flood of large IOs as the servers dump their memory. What we've done is allow those large periods of large IOs to not only use the SCM as a write buffer, but also to use some of the QLC capacity in the cluster. So when a cluster is under heavy writes, if I have specified that 50 terabytes of QLC should also be used as write buffer, those large writes will be written to that 50 terabytes of QLC using the same N+2 erasure codes that we use to write to the SCM. This is a burst solution, as you should have been able to tell when I said I specified 50 terabytes. You set, when you set up the system, declare how big you want the QLC write buffer to be, and size that to be appropriate to the dump that's going to happen. So the default, if you enable this feature, is that the write buffer in QLC will be big enough to hold 5 minutes of writes at the new maximum performance. That's twice as fast as when we didn't have the QLC spillover feature. The reason QLC spillover is so powerful is while each QLC SSD in your cluster is slower than each SCM SSD in your cluster, there are many more QLC SSDs than there are SCM SSDs. And so by spreading this write across many more QLCs, we get much more aggregate bandwidth. Be aware, this is a burst solution, even though typically in computing, when we talk about bursts, we're talking about events that last seconds. And here we're talking about events that last minutes. There's still only a limited amount of space. And when you fill that up, performance is going to fall off. Also, once this large write burst ends, there's a hangover in the system as it starts migrating data from both the SCM and the new QLC write buffer into the fully erasure-coded QLC main repository. So you'll see a system that provides double its write performance for 10 or 15 minutes, and then for the next 10 or 15 minutes runs at its normal rate and then comes back to a little bit faster. So as you see from the chart, we have a substantial increase in write performance across the last few releases. And note that all of this improvement comes from software. While all of these features may not be available to you today, they will be in a relatively short period of time without you having to upgrade your hardware, without having to do a hardware refresh, without all of that expense and complexity. The next big piece for 5.2 is synchronous replication. We've had asynchronous point-in-time replication in the VAST Data platform for a while, but that only allows you to achieve a recovery point objective of about twice the replication period. If I tell the system to replicate every 15 minutes, then I can be relatively confident that should something go wrong, I can recover to a point in time 30 minutes ago. That's great for a lot of applications. Not nearly good enough for many other applications. If you have data coming into your system that has to be saved and that will just be lost if the system goes down or part of the system goes down, the only real solution is synchronous replication. And what synchronous replication means is that when you write data to one cluster, that cluster writes the data to the other cluster in the pair, receives an acknowledgement from the second cluster, and only then acknowledges the write to your application. So by the time that the application has received its ACK, all the data is safe on two clusters. And if an asteroid falls out of the sky and turns your primary data center into a crater, your data is safe in your secondary data center. Note, this means that WAN latency is added to write performance. So if you can write to a local cluster and get 1 millisecond response time, but there's 5 milliseconds of round trip delay between your two clusters, that 1 millisecond latency is going to go up to 6 milliseconds latency. Now, unlike many synchronous replication solutions, we don't have low limits on how much latency you can have between those two systems. So as long as you're willing to deal with that write latency penalty, you can have them spread very far apart and have many milliseconds of latency. This would allow cloud providers to provide regional as opposed to zonal storage by having clusters in 2 zones within the region. It's an active-active model, so you can write to either cluster and be sure that both clusters have all of the data. But be very clear, in 5.2, this is a solution to data durability. It's not a solution to data availability yet. We only have manual failover. We don't have an external quorum or witness noticing that things failed over and noticing that one of the clusters failed and automatically failing over to the survivor. And in 5.2, this is a solution just for S3. Other protocols will come in future releases. So global access is the VAST global namespace and an important part of the VAST data space. The whole idea behind global access is that we can deliver local performance to data in a folder at multiple VAST clusters in multiple locations, including the cloud. That we can allow writes to those shared folders across all of the sites where those folders are available, and that we can have true global consistency of that data. So for any given folder, satellites, the clusters in the diagram that have folder names in pink, hold a cached copy of the folder. As users or applications in New York access the media and renders folders, the New York cluster will fetch that data from the LA and cloud clusters as needed, store it on its local SSDs, make it available to those users. The folders in blue are the origin for that set of data. And so Los Angeles holds a full set of the data in the media folder. The GPU servers in the cloud read selected files, render them, and write the results to the renders folder that's stored in the cloud, where there's a full copy in the cloud cluster, but all of that data is available in all the locations. And it's all strictly consistent. Anytime you do a write, writes are proxied from your local cluster to the origin for the given folder. So all writes occur at the origin. If someone in New York writes to the media folder and someone in the cloud adjacent cluster tries to read it, even if there is a cached copy of that file in the cloud adjacent cluster, the cluster will determine that there is a newer version of some of that data and fetch the updates before presenting the data. So users always see the latest copy of data. Most global namespaces use what's called eventual consistency, where if two users try and write to the same file at roughly the same time, the later writer wins. And the updates that the first writer made will get overwritten. And there's probably a version of the file, but you have to manually merge the changes between the two versions. In 5.2, we're adding support for SMB to global access. So you can now use SMB to access data in satellites. And we're adding the ability to control how satellites pre-fetch data. You can specify for any given folder that a cluster is a satellite for, that this folder should pre-fetch all of the data and metadata. So when anybody at any location makes an update to that folder, make sure we get it as fast as possible so that all of the dailies are preloaded into the New York cluster so executives can view them without waiting for them to transfer over the WAN, because executives have no patience. We can also say just push the metadata so that any changes to metadata get sent to all the satellites immediately, and then the actual data gets sent as you're accessing it. We have had VAST on Cloud in AWS for about 6 months. And VAST on Cloud lets you run, in AWS, lets you run a single AWS instance as a VAST cluster. And that's useful if you're going to be using that as an element in global access. But it's of very limited size. In GCP, we're now supporting full VAST clusters. And so, like any other cluster running on an eBox style technology without HAD boxes, there's a minimum of 11 nodes, so we can distribute erasure codes, protect data against failures of the instances. We leverage GCP's rack awareness, so each of the nodes is in a different rack, enhancing availability. It's a private offer on the Google platform marketplace, so customers who are using Google can set up the instances, but they have to deal with their vast sales team to get the licenses for that. The ideal use case is where customers are already using VAST and GCP, or where they need some ability to do cloud bursting to GCP. Clusters will be available in AWS at an unspecified date and in other cloud providers based on demand. Which brings us to data store updates. The first, which is significant, not that we're doing anything especially imaginative, this is a standard S3 feature, but that it is the first component of the trigger mechanism for the VAST data engine, and that's S3 event publishing. When a user creates or deletes an object that will trigger an event, that event will write an entry into a Kafka compatible event broker using the Kafka provider API. Today, customers are going to have to provide their own Kafka event brokers. In a spoiler for 5.3, a fully Kafka API compatible event broker will be rolled into the VAST data engine and therefore the VAST data platform, so that we'll both receive and manage these events. File and other event triggers are coming next year, along with the ability to actually run functions based on those triggers. The other change in the data store is to extend quotas and quality of service to tenants as well as users and folders. Our cloud provider customers have wanted to be able to set a quota for a tenant, even though they may have multiple quotas for that tenant's own customers. And so this allows cloud service providers to more easily manage their environment. In the VAST database, we have two significant updates. The first is database replication. This extends VAST's asynchronous point-in-time, sometimes called native replication, to views that contain VAST tables. The big deal about database replication is that database replication preserves data consistency. With a typical storage system doing snapshots and/or replications of a database, those snapshots and the data that's being replicated are what we euphemistically call crash consistent. That is, the data within the snapshot is as consistent as if the server running that application crashed and didn't have time to write its data out. The VAST database replication replicates data consistently. If you replicate a view that contains VAST tables, when those tables are replicated, any transactions that were complete against those tables at the time of the replication will be replicated, and they'll be reflected in the copy at the target location. Any transactions that were in progress and only partially posted to this table will be excluded and will not be replicated. So the table will be replicated in a state that is fully consistent at exactly what a user would see if they queried the table at the moment of the snapshot. All you have to do is set a protection policy on a view holding tables, tell it to replicate every X minutes, and you're covered, and that data is now protected consistently. Since fast snapshots are available read-only on the target, it also allows access to those databases from the target location. The other enhancement is a very simple method for importing tables that are currently stored as Parquet files in a customer's existing data lake into the VAST database. Much of the interest in the VAST database is about Hadoop modernization, where they've been using Hadoop with Spark or Trino and some other tools to access data that they've been storing in an object store in Parquet. By importing that data into the VAST database, they get substantial performance and efficiency advantages. But before 5.2, you'd have to do that using Spark or Trino. We now have a simple import function in the GUI. You point it at a folder containing Parquet files, and that data is imported into a new or a existing VAST database table. That brings me to the end of my scheduled presentation. Thanks so much for joining us. Please join us weekly on Tuesdays and Thursdays for our weekly live demo. So let me turn to questions. What is the minimum protection objective of database replication protection? The database replication is just a function of VAST asynchronous replication, and you could set it as low as every 15 seconds. My experience has been that applications either need to be protected every 10 or 15 minutes, or they need synchronous replication, that being able to go back to a 1 minute point isn't that much more useful than going back 10 minutes if you know there's some data lost for most applications. Why can't I make it? Oh. Could I please clarify the throughput speed increases again? So in 5.0, a cluster of Series D boxes could deliver approximately 5.5 gigabytes per second per D box. In 5.1, we added write buffer erasure coding, which took that to approximately 12 gigabytes per second per D box. In 5.2, we add we add write buffer spillover into QLC, and that again doubles performance to about 24 gigabytes per second per D box. All of these improvements are to write performance. Read performance remains the same because we had optimized for read performance originally. And yes, the slides will be made available. Well, folks, it's been a pleasure.
Thank you so much, Howard. I appreciate you being on and explaining that. If anybody has questions, to reach out to us. You can email hello@vastdata or Analia@vastdata. and we will be answer anything that we can. For more information, feel free to join our live demos. We do them weekly on Tuesdays and Thursdays. Just go to vastdata.com/demo. Thank you so much, everyone.
So long, folks.